In the previous lecture, we discussed three approximation methods to determine the area under a curve fx and lying within a particular interval. So we used the right endpoint approximation method, we had the left endpoint approximation, and we considered the midpoint approximation method. In each of the three cases, we saw that for the right end and the left end, we could get either an overestimate value of the graph or an underestimate value for the area. And it was the midpoint approximation which gave us a very good approximation for its value was closer to the actual area. So building on the same idea, well, let's talk about the midpoint approximation again. So for this, what we'll need to do, we'll consider the graph of a particular function. We will consider the graph of f of x, and this graph is going to be positive on the interval a, b, meaning this graph will be lying above the x-axis. So our graph, let's say it has a shape of this particular form. Now what I want to do is find the area under this curve lying within the interval a and b. So what we'll do, we will divide the area under the curve into several rectangles of equal width. Here we have considered n rectangles. So there will be n rectangles, each of equal width delta x. And delta x can be obtained by b minus a divided by n. So here, clearly when we use this formula, then delta x is going to be of equal length. Each width of each rectangle is going to be equal. However, it's not necessary that we choose equal length of delta x, but that will make our calculation much easier. So in the midpoint approximation, all we have to do is consider the first rectangle. Before that, we'll also talk about the endpoints of the subinterval. So this endpoint a, which is x0. Then the next interval endpoint is x1. Next one is x2, x3. This goes all the way up to xn minus 1, xn. So here, x0, this is the endpoint, the beginning of the endpoint of the first rectangle. So this is actually a. Then we have x1. So x1 is a plus delta x. x2 will be a plus 2 times delta x. And we can go all the way up to x n minus 1, which is a plus n minus 1 times delta x, and xn will be a plus n times delta x, which is the endpoint b. Now, what we'll do, we'll consider the endpoint x0 and x1 and consider a new point which is somewhere in between x0 and x1, and we call it x star. So this will be the point corresponding to x1 star, and we will draw a rectangle such that this rectangle passes through the point x1 star. So this is going to be a first rectangle. Then we consider another point x2 star, which is going to lie between x1 and x2. So this is x2 star. We consider the point x2 star on the curve between x1 and x2 and draw a rectangle which passes through this point x2. So we do this for all the rectangles. So this final point will be xn star. So this point is our xn star. So what we'll do next is find the area of each of this rectangle and sum them up within this interval a and b, and that is going to give us the area under the curve. So we have the area, which is approximately, this is not exactly equal. So we have for the first rectangle, delta x is the width multiplied to its height. So its height will be f x1 star plus delta x multiplied to the height of the second rectangle, which will be f of x2 star. Why f of x1 star or f2 star? Because if we look at the diagram, this is going to be the height of the rectangle. So its corresponding height, or the y value, this is going to be f x1 star. For the second rectangle, this is going to be its height, which will be f of x2 star. So if we complete the entire sum, so we will have delta x times f of xn star. So what we can do, we can use the summation notation to approximate this entire sum. So this will be summation delta x multiplied to f x I star, where I is going from 1 to n. So this is the area A, and what we have obtained here is referred to as the Reimann sum. And if we want a very good approximation that is as close as possible to the original value, then our area A will be equals to, we'll take the limit n approaching infinity, where n refers to the number of rectangles that we have chosen. So that means higher the number of rectangles, then closer will be the value of this sum, the Reimann sum, to the original area f xi star. So this is the Reimann sum, and this will help us to find out the area under the given curve for the interval a and b. So we will use the Reimann sum to approximate the area under the curve f of x is equals to x on the interval 0 to 3. Fx equals to x, this is a straight line which passes through the origin. All we have to do is consider the interval 0 and 3. We need to find the area under this curve and between the interval 0 and 3. For that, we are going to consider rectangles of n subintervals, and we find out the area of each of this rectangle by using the midpoint approximation, and once we've done that, we add them to get the area under the curve. So we have, so here delta x represents the width of each rectangle, which will be 3 minus 0 divided by n. Here we will consider n subintervals. So it's 3 over n. This is going to be the height of our first rectangle. This is the height of our second rectangle. And this is going to be the height of our nth rectangle. We'll consider this as the kth rectangle. Fine. So let's consider the first rectangle. For the first rectangle, height will be f of a plus delta x over 2. So this is equals to f of, so our a value is 0 plus delta x, which is 3 over n. So we have 3 over 2n. This will be f of 3 over 2n. Then when you consider the second rectangle, so that will be f of a plus 3 times delta x over 2. And this is going to give us f of 9 over 2n. So if we continue, then the kth rectangle, so that will be f of 2k minus 1 over 2 times delta x. So our delta x will be 3 over n. So this is going to be the height of our kth rectangle. So what we'll do, we'll sum all of them by multiplying each of them with the width delta x. So our Reimann sum Rn, that will be approximately summation. We are considering k rectangles, so we have k going from 1 to n. Let's first write down the formula. We have delta x times f of the kth, the height of the kth rectangle, 2k minus 1 divided by 2 times 3 over n. Right. So let's substitute the value. So we have the summation going from k equals to 1 to n. We have delta x, so delta x will be 3 over n. Our function is given by f of x is equals to x. So f of 2k minus 1 over 2 times 3 over n, this will be simply 2k minus 1 over 2 times 3 over n. So we'll have to find a summation. So this will be, so we are summing over k, so we can take the n to the n outside of the summation. This will be 3 times 3, so this is 9 divided by 2n squared. And within the summation, we have k from going from 1 to n, 2k minus 1. Right. So let's find out this summation. So we have 9 over 2n squared. This will be summation 2 times summation of k minus summation of 1, with k going from 1 to n. So our Rn is 9 over 2n squared. So this summation, this is simply n times n plus 1 divided by 2 minus summation of 1, with key going from 1 to n, this will be simply n. So the 2 and 2 goes away. So we have 9 over 2 n squared. And within we have n squared plus n minus n. So the n and n goes away. So this leaves us with Rn approximately 9 over 2n squared times n squared. So the n squared and n squared also goes away. So the Riemann sum is giving us 9 over 2. And if we take the limit n approaching infinity, an extremely large subinterval, then Rn, this is going to give us the approximate, and this is going to give us the area A, whose value will be 9 over 2 square units. So this is the area under the curve of fx equals to x and the interval 0 to 3, the value of 9 over 2 square units. Now that we have the Riemann sum which gives us the area, that is limit n approaching infinity, an extremely large number with summation n going from summation k going from 1 to n, just given by f of x k star delta x. So this actually is similar to the summation. When we have the n value going to an extremely large number, then the summation sign can be changed to an integral sign. So we have integral f of x, and this delta x then becomes the elemental length dx, and our limit will be from a to b, and this becomes the definition of a definite integral. Next, we have the fundamental theorem of calculus. The fundamental theorem of calculus states that if we have an integral with the limits going from a to b, fx dx, then we can obtain a function f of x. This f of x is going to be the entire derivative of f of x. Then we can calculate this value at the n points. Then we have f of b minus f of a. Let's try to apply the fundamental theorem of calculus on a function x. So let's say we have the integral x dx with the limits going from 0 to 3. So we have to think of a function whose derivative is x. So a function whose derivative is x is going to be x squared over 2. We can check it out. Derivative with respect to x of x squared over 2. So that will be half times derivative with respect to x of x squared. Derivative of x squared is 2x. So we have 2x over 2. That gives us x. So a new function x squared over 2 is going to be the entire derivative of our function x. Now once we have this, we can use the fundamental theorem of calculus and use it to obtain the value of this particular integral. The function x squared over 2, all we have to do is calculate its value at the n points. So that means this is referred to as the upper limit, and this is going to be our lower limit, or usually the n point. So we'll always start with the upper limit. So that means we have x squared over 2. What we'll do, in place of x, we'll replace with the upper limit value, which is 3. So we have 3 squared over 2 minus, then we replace the value of x with the lower limit value, which is 0. So we have 0 squared over 2, and this gives us 9 over 2. And this was exactly what we obtained in the previous problem in the Riemann sum. This was the same problem. So using the Riemann sum, we obtained 9 over 2, and using the fundamental theorem of calculus, we also obtained 9 over 2. Let us consider another problem. So what will be the integration, the definite integral of, let's say, 4 times cosine of x dx with the limits going from 0 to pi over 2. We have to think of a function whose derivative is 4 times cosine of x. So what kind of a function we could have? So if we take 4 sine x, so derivative of 4 sine x is 4 cosine of x. Now that we have that value, all we have to do is now calculate the value of this function at the n point. So we'll begin with the upper value. So this will be 4 times sine pi over 2 minus 4 times sine 0. So what we have done, in place of x, we have replaced with the upper limit and the lower limit. The sine pi over 2, so that's 1. So we have 4 times 1 minus 4 times sine 0 is 0. So this is giving us a value 4. So this is how we can use the fundamental theorem of calculus, which is only applicable to definite integral. So this is referred to as a definite integral. Definite integral means when the endpoints are defined or they are specified. In the next lecture, we will be talking about indefinite integrals. So indefinite integrals are integrals whose endpoints are not defined. And we'll be looking at some techniques how to solve different types of integrals. So see you in the next class.